Hey everyone, it's Alan. Hope everyone's doing well. Um, this next installment in the video series is called the Law of Cosines. Now that we've gone through both in depth and derived the law of sines, and then looked at its special cases, namely the ambiguous case, spent an entire video on that. We're now going to switch gears to when we can't use the law of sines. And so this next one, obviously, which goes hand in hand, would be the law of cosines. And so I'll talk to you a little bit about that, derive it, show you where it came from, learn how to use it, and that's a wrap. So here we go. So the first thing we're going to look at is obviously still trying to solve oblique triangles, but now we're going to be looking at when we have two sides and only one angle. And so we're looking at the side angle side and the side side scenario. We already talked about the ASS scenario, but now we have the included angle, the angle in between our two sides. And so unfortunately, we're not able to use the law of sines. Could be 0, 1, or even two separate scenarios for triangles. But now we're going to be talking about this law of cosines, and it doesn't have an ambiguous case, fortunately. When we're given the side and an included angle and another side, there's no way that we can take and move one of those two sides that we know because the angle in between it is already there and stationary. We can't move that at all. And so there's no ambiguous case like the law of sines. So that's a good thing. But there is a special case still with the law of cosines, and that is, if you can see, when we have a side scenario, because then we don't have any angles. And we haven't been told the angles yet. And therefore, we have to make sure that even though they gave us three sides and they're asking us to find the three angles, we got to make sure that there even exists a triangle with those three sides. So I've mentioned it before in a previous video, but it's called the triangle inequality theorem that we're going to utilize for this scenario. And so I just gave you a little breakdown of, let's say we had a triangle with lengths 3, 5, and 10. Well, if you remember, according to the triangle inequality theorem, is that if we take any two sides, namely we wanted to look at the smallest of the two, and add them, they had to be strictly greater than the third side, which in this case, we want to compare it to the largest. So I took and I measured out, let's say about 10 centimeters. And then on either side, I want to try to create a triangle of that 10 centimeters. I want to take from one end and the other my other two lengths, one of 3 centimeters and the other of 5 centimeters. And I want to take those and I want to try to push them down and pivot them around their vertex and see if I can actually make a triangle. And if you can see that if I was to push this angle, or excuse me, this side of 3 all the way down, it would still only be a length of 3 centimeters. And if I did the same thing with the 5 centimeters, hopefully you can see that this length would be 5 still, which unfortunately only gives us 8, which means we are 2 centimeters short from even connecting because of the length of 10 on the base and the bottom down there. So that's why if we were to take the 3 plus 5 and see if it was strictly greater than the third side, we can see that 8 is not greater than 10, which is why we cannot make a triangle. So like I've already mentioned before in a previous video, hopefully you recognize this one more time, because if we are given three sides and they're telling us to find the three angles, and two of our sides, again, namely the smaller two, when we add them up, are not strictly greater than the largest side, then we can't even formulate a triangle, and therefore we don't even have to find the angles because they don't exist. So that is the one special case that we're going to be possibly dealing with for the law of cosine scenario, and that's when we have side, or three side lengths given. So let's take a look at how to derive and what the law of cosines is. Now, again, I'm only going to do it for one scenario and then just kind of say, well, if I switched around point A, point B, and point C, then we'd get a different case. So in this, I'm going to take and label the lengths of each one of these sides according to the opposite angle that formulates it. So in this case, angle A here, if I was to stretch it out on both ends and connect there, then that would be side length A. And opposite B would be this one. Opposite the angle C would be this side C there. And hopefully you can see that I have my oblique triangle that I'm trying to solve for. Now, again, we're going to be given a side, angle side, or all three sides. So we'll get into that in a minute. But in order to derive the law of sines or cosines, remember the only way that we can use any trig function is with a right triangle. And this obviously is not one. So the first thing I'm going to do before I get to that is I'm going to label my origin there on my axes, my x and my y axis at 0, 0. And then this point C here would actually be a length of A to get here, and then up and down 0. Now, the only one that's a little wishy-washy is point A that I've put over there to the left, which to get there, I'd have to go left some x value, and then up some y value. So this would be the point x comma y. Now, if you notice, I just formed a right triangle off to the side there. Okay, if you want to label this as some other point, we can call it point D or whatever. But now I have a right triangle ADB or ABD. And so I can now use my law of sines and cosines. And if I don't want to keep that x value and that y value because we already have A, B, and C's as side lengths of my original triangle in blue there, then I don't know if you guys remember this, we need to figure out what x and what y are equal to so that I can rewrite this point over here as a different looking point, x comma y. And in order to do that, I'm going to utilize this angle B here that we formed in this right triangle. And if you remember, if you were to take the cosine of that angle B, then I would have the adjacent, which is x, over the hypotenuse, which would be the length C. And if I took the sine of angle B, then I would have the opposite over the hypotenuse. And now hopefully you can see that I would be able to solve each of those for the x and the y by simply multiplying over by the length or lowercase c to both sides. And that would then enable me to find what x is equal to and what the y is equal to, which then allows me to rewrite my x and my y as c times cosine of b and c times the sine of b. So now I have all three of my original points, A, B, and C, in terms of A's, B's, and C's, and not those additional X's and Y's that we didn't want to add in. So what we are going to do here is we're going to utilize an old formula that hopefully you guys remember, which is called the distance formula. And I'm going to find the distance from point A to point C, from here all the way to here. And hopefully you notice that is the length of B. But just to remind you that the distance formula is equal to the square root of the difference in my x value squared plus the difference in my y value squared. So what I'm going to do is now use this in our terms that we have for this triangle, which instead of the distance between any 2 points, we said we wanted to find it on that longest side, which was letter B. So I'm going to replace that with B, and then I'm going to have to take this and rewrite it all. So my x2 would be here's my x and my y, and here's my other x and my other y. And I'm going to call this my first point, and I'm going to call this my second point, and then I'm going to plug those things in to my distance formula. So I will get a big x2, which we said was c times the cosine of b, minus x1, which was a. And that whole thing would be squared, plus, then I'll take the y2, which was little c times the sine of b, and subtract y1, which was 0. Now, unfortunately, that means that I have to square this thing out in order to actually find what b is equal to. So going off to the side, I'd have to take c times the cosine of angle b minus a times itself, squaring it. And if you do a little bit of foiling, distributing, hopefully you'll notice that I'd have this times that, which is going to give me little c squared times the cosine of b squared. Then I'd have to multiply that times the negative a, which is going to give me negative a times c times the cosine of angle b. And then when I do it again right here, and I distribute the negative a to that, I'm going to get the same value, which means I'm just going to have negative 2 of those. And then lastly, a negative a times negative a is positive a squared. And that is what this whole thing happens to be. C squared times cosine squared b minus 2ac times the cosine of b plus a squared. And that, unfortunately, is the ugliest part of this mess. But we also have the c sine b minus 0 squared. And since that is subtracting by 0, we will just square that and get plus c squared times the sine squared of angle b. Now, writing that big old nasty long square root is kind of laborsome, and I don't want to do it anymore. So what we're going to do to get rid of that is we're actually going to just take and square both sides so that we don't have to write that anymore. So now I got b squared equals, and I can get rid of the square root. Now, hopefully you also notice that there are cosine squareds and sine squareds involved. And as soon as you see trig functions that are squared, hopefully an alarm goes off in your mind and you immediately start thinking of the Pythagorean identities. Now, unfortunately, they are multiplied both by c squared, but that's no problem because hopefully you also remember that we can factor that c squared out, and that would allow us to just have cosine squared of angle b plus the sine squared of angle b. And then bringing down the rest of the stuff still, we got negative 2ac times the cosine of angle b plus an a squared. Now, the reason we did the whole factoring out of c squared was to try to isolate and hopefully replace with something simpler, like the Pythagorean identity of sine squared plus cosine squared of the same angle. It's always equal to, hopefully you said it, 1. Because now we know 1 times c squared just gives us c squared. Now I'm going to take this a squared and write it in front as well. And then I'm going to put minus 2 times the AC times the cosine of b. And remember, that was all equal to b squared. And that, my friends, is what is called the law of cosines. Now, don't forget, this only has A's, B's, and C's involved. So let me show you very quickly what that entails if we were to have these specifically, A, little b, and C. Now, obviously, little b is here, and that's the one that is equal to, so that's what we're trying to find. But if we had little a, little c, which are my other two side lengths, and if you notice, the only other thing that isn't a little a or a little c was the angle of b. And that angle right here is what is called the included angle. So again, this would be one of those cases where we have the side, the angle included in between the other side. So this is a side angle side scenario that allows us to find the other side. For my example that I wrote A, B's, and C's, that would be for letter B. So of course, this can work by just changing around the letters. But one thing I want to make sure that you notice is that we have to have side angle side. And here are the other versions of that if you wanted to find little a or side length A, side length B, or side length C. You need to know the other two sides that you would use twice, and then the included angle, the angle that goes along with the side that you're trying to find. Right? So when we are going to use this is for the side angle side. We can actually also use this when we have side, side, side. But then we would want to move some of this stuff over. So I'm going to show you one of those right now as well. And I'll just do it for the first up there. So if we had a squared equals b squared plus c squared, very similar to our Pythagorean theorem, except we're going to have -2 times those two values that we know, as well as multiplied times the cosine of the angle for the side length that we were trying to find. So what I want to do is, if I had side, side, side involved, then I know little a, little b, and little c. So therefore, I want to solve this equation for angle A. And so that I don't have to do this every single time, I'm just going to write this down and then show you the other versions of it by changing around its letters. And then that way we can put it in our notes and hopefully start to memorize it. So the first step I'm going to do is, if you guys can handle a multiple step process, I'm going to subtract b squared to both sides of my equation and c squared. I won't do too many at once. So that will cancel out my b squared and c squared. And that would leave me with an a squared minus b squared minus c squared on one side of my equation, and then -2bc times the cosine of angle A on the other. So since I'm trying to get A by itself, my next step would be to undo this multiplying by dividing by a -2bc to both sides. Now we know what happens when we divide by a negative to a negative, that becomes a positive. And when we divide anything by itself, it becomes a 1. So I now have the cosine of angle A is equal to this. Now, the one thing that we don't typically like is to divide by negatives, just like we don't like dividing by square roots or imaginary numbers. So the only thing I'm going to do is take this negative. I'm going to leave the 2 in the BC because I can't divide that. I would have to do it into each one of these things. So I'm going to take that negative and I'm going to divide it into each and every one, which is just going to change the sign to every single one of those things. So the B will now become positive, the C will become positive, and then the A will be the one that we're going to end up subtracting. Let me bring that down so that you can all see it. My apologies. And then we had all of that over our 2BC, and that way we don't have a negative down there. No big deal, but it's just a little bit simpler looking when we don't. So this would be the alternate version of the law of cosines that allows us to solve for an angle. And of course, if we're going to be solving for an angle, we're going to have to use the inverse in order to actually find it. Okay, so hopefully you can see the patterns that we've been dealing with here, and maybe even give me the cosine of angle B for my law of cosines. What would change as far as the letters go? Well, hopefully you notice the A's are only written once. Everything else is going to be there. So I'm going to have the a squared plus c squared minus b squared this time, all over to ac. And that would be my other version for that. And then based off of that, I'm hoping that you guys could come up with how we would find angle C. And that would be a squared plus b squared minus the angle side c squared over 2ab. And these are worth noting, even though the book doesn't include them in it, all right? Because then when we're trying to find an angle and we are given three sides, then we can utilize any one of these and not have to go through all of this that I did over here. I can just jump to this as long as I memorize them. All right, so again, I wanted to show you where the law of cosines came from, why it is what it is, why unfortunately it's a little bit more involved in the law of sines. But I do have good news for you. The only thing that you will do the law of cosines for are these two scenarios, and you will only ever have to use the law of cosines once. Where unfortunately, with the law of sines, sometimes we had to use it 2 and 3 times. So the good news is twofold. One, we only have to ever use this formula, whichever one, depending on what we're trying to find. And we'd have to take the square root to get the A, or the B, or the C. And there is no ambiguous case with the law of cosines. So we'd only ever have to use the law of cosines once, and we don't have to worry about if there's two possible cases or triangles. There's only ever going to be one, given a side, angle, side, or a side, 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 as long as those three sides create a triangle, which we talked about at the very beginning. All right, so that's the gist of it. Now we're going to get into some examples and see how we can work these things out. So the first one here, going to look exactly like all of our other problems, which is going to be a little bit more difficult when you get to the quizzes or the tests, because all of these are going to look the same. And so what did we learn first? The law of sines. And why did we learn it first? Because it's simpler. Then that's what I would always look for first. And how am I going to know if this is a law of sines or law of cosines? Do I have to remember it's an SAS or an ASS or any of those? No. Don't SMH. All you have to do is take and look for that good ratio. And that good ratio is when we had an angle and a side of the same letter. And as you can see here, we only have a B, an A, and a C. Don't even really need to draw it out. All I know is that I cannot use the law of sines in the form that this is given. Now, if I had two angles, I could actually find the third and possibly use the law of sines rather than having to go the law of cosines route, which is, as we saw, a little bit more detailed. So what I'm going to do is, because I now have angle B, I would really like to know side length B, or little b, so that I could then use the law of sines and hopefully be on my way. So how I'm going to set this up is, I'll write it down one more time in general, and then we'll plug it all in and go to work. But I'm going to write little b squared is equal to, hopefully you remember, a squared plus c squared, the other two letters, minus 2 times those things, also times the cosine of the angle of the side you're trying to find, in this case, B. Now, of course, we're going to have to take the square root of this whole mess at the end, but I'm going to wait until the end because I don't want to write a big old nasty long square root a bunch of times. So plugging this all in, I will then take and calculate this all out. The A they gave us was 28.2, which will both go there and there. The C, which is 46.7, which goes in those two slots. And then my angle B, which is 73.5 degrees. All I got to do is a big, nasty calculation with this, and be very, very careful. If you try to do all this in one, remember, calculators can only calculate. Computers only compute. They cannot think for you. They will do the order of operations in the order that you put this in. So my suggestion to you is to work this from right to left. So the way that I'm going to plug this into my calculator, let me pull that up real quick for you, is I'm going to do the cosine of the 73.5. I'm going to find what that is, and then I'm going to multiply it times the 46.7, the 28.2, and the negative 2. 46.7, 28.2, and make sure you put negative 2, not minus 2. So make sure you find that in the proper place. Hit equals. Then don't forget, we're going to add to that our 46.7 squared plus, then we're going to add the 28.2 squared. Now that seems like an awfully big number, and that's because it is. Because don't forget, what do we still have to do to that whole thing in order to find what b is? And hopefully you said it. We have to take the square root of that whole thing. Okay, so in order to figure out what b actually is, I will take that answer and I will take the square root of that whole thing. And that gives me 47.2. Now don't forget, when you square your units and you multiply times, you would also have that squared. So we would have had feet squared, but when we take the square root of something that's squared, we get out our distance that we wanted, which in this case was feet. So we get 47.2 feet, which now allows us to utilize our law of sines with angle B to find both angle A and angle C, which were the last two parts that we needed to know. All right, so going back real quick to our law of sines, hopefully you remember it by now. We will take, since we're trying to find angles, the sine of angle A over little a, which is 28.2 feet. And I will put it over the sine of angle B, which was the one and only angle we were given, over what we had to work to find using our law of cosines, little or side B, 47.2. And like we've done multiple times, we will now take and get rid of that 28.2 on bottom by multiplying both sides by that to cancel that out and get the sine of angle A. Now don't forget, that allows us to actually take this big old nasty number, and in order to find an angle, we have to utilize our inverse function, which will then take the input and the output and reverse their order, which will then allow us to find what angle A is. And in doing all that, plugging it in your calculator, you will get a 34.9 degree angle. Do you have to use the law of sines again and do that for angle C? The good news is, no, you do not. Because we know that angle A plus angle B plus angle C is all equal to 180, and we now have angles A and B, we will just subtract each of those to figure out what angle C is from 180. And if you do that, you would come out with an answer of 71.6 degrees. So not too bad. Hopefully with me skipping a few of the calculations that we've already been practicing working on for the law of sines, you were okay doing that off to the side, pausing the video and doing it on your own. But otherwise, pretty straightforward. It's just law of cosines, a lot more in depth. And remember, notice I only used it one time. Then I was able to utilize my law of sines here. And once I had that, I then had 2 out of my 3 angles, which I know the sum of that is 180. And I was able to find the last missing piece in order to solve that triangle. But here's one more thing that we talked about earlier on when we first learned the law of sines, and that was how to find the area. Now, the other one that we found the area of was our typical 1/2 base times height, but that was only for right triangles. So then we came up with that alternate version where we actually used our law of sines and went and tried to find it. Well, there's a Greek philosopher, mathematician named Heron that actually came up with a very ingenious way to find the area of a triangle, any triangle, when you are only given 3 sides. Now, I'm not going to derive this one for you simply because it's very labor intensive and I don't think it would do you guys that much good because we're not going to use the area when we have 3 sides a whole lot like we will as we continue on with this class for the law of sines and the law of cosines. which is why I took the time to derive those. So for this one, I'm just going to quickly explain it. We'll do an example, make sure that you got it down, and then you guys just need to practice. He came up with a way to find this length of S, which he called the semi-perimeter. Now, you know a semicircle to be half of a circle. So the semi-perimeter is when we take the perimeter of this whole thing by adding up all three sides, and then we take half of it. His formula to find the area of a triangle with three known sides, that is a non-right triangle, is this. You have to take the square root of the semi-perimeter, and then you got to find the difference of the semi-perimeter with each one of your side lengths, and then multiply all four of those things together, and then take the square root, and that will always give you the area. So again, if you want to check it out, then you can look it up on another video or even in our book, and most books will have the derivation of it. I just don't think it's worth our time.